Mic check, yeah. Hello there, I'm Markku-Juhani Saarinen, so with PQShield and University of Tampere now, most of the time. So anyway, I'm the chair of the post-quantum task group that just stood up, just got started. So first, a little recap of the standards. So in many ways, post-quantum crypto is a cryptographic modernization program. I'll cover the requirements here. Then there's a bit about quantitative analysis. I'm doing a very textbook quantitative analysis of these algorithms in order to motivate the instruction choices that we are making. And the last section has a couple of instructions that we think are helpful. These are currently considered in the task group, but not finalized in any sense. So 1 minute introduction, that's really 1 minute. So post-quantum crypto is new crypto. So it runs on any CPU, by secure against quantum attacks. All crypto designed in last 15 years is basically post-quantum at the moment. And the motivation is, of course, that we know that once we have a quantum computer, you can factor numbers in polynomial time, you can solve elliptic curve, discrete log, which means that all asymmetric crypto becomes more or less vulnerable. And these attacks are polynomial time, so it doesn't help growing the key size because you can just grow the quantum computer and you are unlikely to win that competition. So that's the motivation for post-quantum crypto. Now, this is very much a standards-driven thing. So this is, in some quarters, this is a cryptographic modernization program. Basically, we are replacing old algorithms with new algorithms. We are replacing in TLS, for example, the Diffie-Hellman key exchange with Kyber. That's also usable for public key encryption, like an email type setting. Then we have dilithium, which is the main algorithm for signatures. So that's for authentication and your certificates and such things. And then there was a third algorithm selected, which is a stateless hash-based signature scheme, which Sphinx Plus. So that would be useful in your root of trust module, perhaps to secure the boot there. It's not very fast for signing, but your verification function is pretty good. So anyway, these already have like FIPS standard numbers for initial public drafts, and there's a pressure to basically replace old algorithms with new algorithms. In some quarters, there's a very specific timeline to do this. Last week, I was in Washington, D.C. for ICCC, and the NSA guy was using this exact slide for the transition. Of course, NSA makes rules only for defense and intelligence community, not for civilian use or even federal use. But there's another sort of like for federal use in the US, there's another presidential memorandum also giving out timelines. So private industry moves at their own pace, but quite often they follow this stuff. But for a RISC-V hardware vendor, if it's a government requirement, you want your chip to be acceptable to government, so you kind of tend to pay attention to these transition timelines. So it doesn't matter if you believe in quantum computers coming on year X or not. This is a requirement. It's a compliance issue, more or less. So this transition timelines, some of them are surprisingly early, like firmware signing, becoming from 25, like in 2 years' time, and that affects things like your secure boot mechanism, for example. Some of these transitions are super easy, like what already happened in Chrome and the Google Cloud, because you can do a software update on your browser and your operating system, and your TLS handshake is fine. As long as the cloud edge talks the same protocol as your device, then you're good. But the hardest things are really the secure boot root of trust side, where we need support. So this the scope of this talk is actually more on the acceleration side. So we are talking about the TLS stack and Linux kernel, software acceleration, not side channel security, which would be on root of trust. That's just the scope of our specific task group here. Now, coming to the quantitative analysis, so we have for Kyber. So I'm focusing on two algorithms, Kyber, the key establishment algorithm, and Dilithium, the signature scheme. So this is for Kyber. I'm looking at two implementations. First is the reference code from the algorithm designers, and also in library PQClean. You can also find it in Single. So there's a Rust wrapper. In September, Single updated their protocol. This is the Single app you have on your phone. Updated their protocol to support Kyber, and it's with this PQXDH thing. It is a Rust wrapper, and the code underneath is the code I'm benchmarking here. Now, the second implementation I'm benchmarking, this is from Boring SSL. So this is a production code in Chrome and also in Android 14. So last month, if you happen to have a phone from Google, it did an auto update to Android 14 perhaps, and you will have this in your phone already. So these are, I believe, fairly realistic benchmarking targets and code. So I'm benchmarking specifically Kyber 768. So there's 3 security levels for Kyber. This one is in the TLS standard. So this is the handshake that happens when you establish a connection. So it's a sum of key generation, NCAPs, and DCAPs. So these are the 3 steps that you do during the handshake. So here we have a little breakdown of the instructions. When you have this code and compile that on a LLVM 18 snapshot, with the vector extension enabled and some other extensions enabled that we believe are in the Android profile, and then you instrument the implementation and see where it's actually spending its time. So on the left, we have the reference code. On the right, we have the boring SSL code. Amazingly, they are consuming almost exactly the same number of instructions both, but the pi diagrams are very different. So it's funny. So one implementation is faster doing other things and slower doing other things, and then you flip it around. But in both cases, it's mostly NTT, number theoretic transform, inverse number theoretic transform, and Ketchuk, which is the cryptographic component underneath SHA-3 and Shake standards. So it's basically all Ketchuk and NTT. The things like base mal there, that's also similar to, that's part actually of NTT multiplication. Then there's a little segment there, which is the rest of the stuff, which is serialization, deserialization, all kind of miscellaneous things that you need to do. Now, talking about Ketchuk, so that's, recall that in the Android implementation, that's actually 2/3 of the cycle are spent doing just this symmetric SHA-3 hashing, so huge chunk. So looking more closely into it, so boring SSL just happens to have a very, very slow Ketchuk implementation in this case. The reference, so that's 11,000 instructions. Reference code does it in 4,000. There's a couple of tricks you can use to increase it. I noticed a funny thing that if I disable the bit manip instructions, which have a rotate and not, I actually lose about 50% of the performance on the reference code, etc. But anyway, the boring SSL code just looked like very much like a placeholder implementation of Ketchuk, because it was actually in the Kyber subdirectory, so it wasn't even like a shared implementation. Apparently, because that stack doesn't use SHA-3 yet much. So there's these anecdotes. But anyway, you can see that it's thousands of instructions, and we are planning of replacing that with a single instruction. So that will, in my mind, speed things up quite a bit, you know, even if they improve their Ketchuk. So the rest of it, basically all of this NTT stuff is modular arithmetic, modulo this 12-bit prime, which is, I think it's fixed in stone now. So we've been evaluating Kyber for many years now. This is not something that we expect to change, so we can treat it like an AESS box. It's a FIPS standard, it's FIPS 203, so we might put that into the instruction itself. And so this is the rest of it. So if we optimize Ketchuk into 0, the rest is basically this stuff, so we want to optimize these two, and we do this by speeding it up. Okay, I realized that I might be going a little, okay, I've got 10 minutes. So entity arithmetic is really modular arithmetic. You are doing additions, subtractions, and multiplications modulo this specific number. So I was looking at the reduction code. So boring SSL uses Barrett reduction. It's on the left. It's just a static function. It's not even defined as inline, which I found impressive. And what I found impressive as well is that LLVM18 auto-vectorizes it to the code on the right. So if you squint your eyes, you might see that the instructions, many of them start with V. They are vector instructions. So it's able to do this magic, turn that code on the left, and the loops in the entity code into auto-vectorized thing. But still, a multiply in that, the Barrett reduction requires about 5 or 6 instructions. So basically, you know, there's a bunch of widening. There's a widening multiplication. There's a shift of some kind. There's an addition, and then there's another multiplication. All in all, it goes down to 5 or 6 instructions. So we need to replace that with a single instruction in order to make things faster. Now, dilithium target coming, it's the optimized C implementation in PQ clean. So OpenSSL doesn't have this yet. So that's why I used the reference implementation and 2 security levels RFA. So this code is actually used by HSM vendors, and there's a IATF 118 going on, you know, IATF meeting where they are looking at like interoperability of certificates and PKI, and many of the HSM vendors who are in that interop actually use this same code underneath. So they're just making sure that their ASN1 stuff like interoperates. The algorithm implementation itself is kind of universally the same. And TLS, of course, uses this for authentication. Quite often, you need a couple of verifications and 1 signature on every handshake. So decreasing the handshake latency, you are optimizing dilithium. It's kind of important there as well. So here's the 2 bits of dilithium. We are not that interested in keygen because that in signatures that's something you do once every few months. But in signing, you do that on every handshake. You are authenticating by signing something, and you are verifying a couple of times. You are verifying a certificate chain and the specific signature in the handshake. So, but anyway, the pie diagram, a little different, but dominated again by Keccak and entity completely. So these are the 2 things also in dilithium that we are optimizing. So yeah, so dilithium instruction mix is similar, but the Q value, the fixed magical prime here is a little different. So you have it in there. It's 23 bits. So typically stored in a 32-bit vector register in your thing. So here I'm making the point that I propose that we fix these new 2 magical primes into the instruction set, our optional extension for all time, so that we can use it. Keccak is of course exactly the same, so that core permutation doesn't change. Now I also did some optimization on dilithium to study like how they are actually doing the Montgomery or Barrett reduction. Montgomery ends up being something like these 6 instructions, these 6 vector instructions, and I would prefer to replace those 6 vector instructions with a single instruction. Also with the feature that we don't use a widening multiplication. So with these instructions, when you are multiplying 2 numbers, like 32-bit numbers, you get a 64-bit result. But with our instruction, you can multiply 2 32-bit numbers and get a 23-bit number, which is the already reduced thing. So that kind of relieves the register pressure, and of course the instruction count goes down, so you are faster, hopefully. Now, so, oops. Oh yeah, now we come to my actual proposals. At the moment, we are looking at proposal 1, which is the integer multiply. Only criticism that one might have for the naming is that Q is sometimes interpreted as a quad word. This has nothing to do with quad word. I just used the letter Q to say that it's this prime Q. But so it's basically a version of the standard vector multiply, or the vector or vector scalar multiply, where internally you are doing this modular reduction. So you get this longer intermediate multiply result, and you reduce it before you output it. So that kind of makes it a lot simpler. Now the question is how to communicate this fixed Q into the ISA. So one option that I might prefer is to use the SEW register to just say that, oh yeah, for these instructions, if you are 16-bit SEW, your vector, then we are using the Kyber modules. If you are 32-bit, then we are using the dilithium module. So that way you don't have to like explain it much further than that. There are other options in the ISA. So vector ISA has, for example, fixed point rounding arithmetic instructions. So perhaps this could be like a rounding mode, you know, if we don't want to invent a new instruction opcode, or it could be something else. There are also multiply add instructions, which kind of combine two instructions into one. Not sure if that would help here a lot, because addition is such that you can add few mod Q numbers and you don't have to reduce at every step. So I feel like one could do with the regular addition and subtraction vector instructions. So the semantics of these are a little bit more complex that I wrote there. So they accept signed inputs, but the output modulus reduction is not your C language modulus reduction, which is weird and non-mathematical because it's negative. So this is a real modulus operator that we are doing here. Anyway, so that's a detail. Now for Ketchak, the other important part, there's been, I can tell you that if you implement this permutation, you can make it really fast. So typically the entire permutation is 24 cycles. Recall that it can be thousands of cycles or instructions in normally. It's a little large. It's about 30,000 gates. It has a very short critical path, but it has lots of wires crossing. So that's the weird part. But anyway, so there's been some academic proposals for it. So some team put the state of the Ketchak accessible through floating point registers, which is not going to fly with the architecture people. I don't think so. Then there's been proposals to split that into multiple instructions each round, but I don't see much point in it because it's simple enough to have a single instruction for it. So the second proposal out of two is this Ketchak permutation instruction, which uses a massive vector register group input, 1600 bits, and spits out another 1600 bits. Now, to me, it seems that most of the time implementing such a thing is gathering these 1600 bits from the vector register group and then putting it back out. So that's why I feel that it should be a multi-round instruction rather than a single round instruction. So that way you are gathering basically the 1600 bits, running 24 rounds, and then putting it out. All in all, that would seem like a little feasible thing to do. We'll have to build it and try it out. Now, so two main suggestions in this task group. We have a single width modular multiply instruction specifically for Kyber and dilithium. And then we have a multi-round Ketchak permutation for a register group, a 1600-bit massive state that's accessed here. Regarding the Ketchak stuff, there's a wide assumption that Ketchak will be used for many things. There's nothing you can do with AES that you can't do with Ketchak, and that's why we think it's a very useful thing in the future. I think I might have time for a single question. There's a single question. 24. Let me see if I can see the 24. Here we are. Next. VZ VLI. So the question is that if I can minimize these VZ VLI things, then that will improve performance. I have wonderful news for you. Yes, we don't need those instructions with this this extension, so those are gone. So, all right, thank you.